Welcome. Today we're going to be talking about the properties of exponents. Now, this can be just regular exponents or rational exponents. Same thing for either of them. The same properties, that is. So when you are multiplying things to a power that have the same base, you add the exponents. When you raise a power to a power, you multiply the exponents. If you have a negative power, move it to the other side of the fraction bar from where it is, whether it's on top or bottom, and it becomes the opposite sign, exponent. Then we have division, and it is the top minus the bottom fraction. If you have a fraction to a power, that power applies to both the top, everything in the top and the bottom of the fraction. If you have a radical with an n for a root, and you have things multiplied inside, that's equivalent to having separate radicals with the same index and multiplication between them. Same for division, and it goes back and forth, by the way. If they're separate, you can put them together. If you're dividing in an n radical, indexed radical, you can write it as separate ones divided, and vice versa. All right, here's our first example. We have cube root of 25 times cube root of negative 5. This is the same as the cube root of 25 times negative 5. Now, the negative, we know, can come out as a negative on the outside. And now we can proceed to reduce or simplify the inside. 25 is 5 times 5, and I've got this 5. I need 3 to pull 1 out. 1, 2, 3 comes out, and the final answer here is negative 5. Here's our next problems. There we go. On the top here, I have separate radicals. I can write that as one fraction. Now, why would I write it as one fraction? First of all, I'd write it as one fraction if I can reduce these two. Like 54 over 9, that simplifies. 9 goes into 54 6 times evenly, so that is the cube root of 6, and that's as far as I can go with that one. We'll talk about rationalizing a little bit later. Now, multiplication, I've got the fifth root of 81 times 3. We know 81 can be broken apart into 9 times 9, and 9 is equal to 3 times 3. And I need 5 to pull 1 out, because the index is 5. So my answer is just 3. There's nothing left over. All right. In your book, please try page 362, 22, and 26. And we'll go over those. I don't know if I did that. Let's see. Let me back up to that. 362. And 26. So if you have the book, 22 is negative 3, 26 is positive 3. Okay. Let's go on to this one. Now, if you don't have the book, I understand. Don't worry about it. Here we go. if I want to simplify this, I'm going to break it apart. Let's see, 2 times 81. And then this is, again, 9 times 9. 3, 3, 3, 3, and a 2. I need 4 to pull one out. 1, 2, 3, 4. I have a 3 on the outside. The 2 is left over. That stays inside. But don't forget your index of 4. Over here, 3 will not go into 56. So here's what I do. How many 3's do I need to pull one out? In this case, 3. How many do I have? 1. How many more do I need? 2. So I have to multiply top and bottom by cube root of 3 times 3 to rationalize this denominator. So I end up, now I should have done this first. You should simplify if you can on the top before you even start. Unfortunately, I already have rushed ahead and done it. So let's see. Cube root 56 times 3 on top over the number 3 on bottom. Well, that's great, but it turns out 56, 7 times 8, and we know 8 is 2 times 2 times 2. So that's a group of 3 2's. I can pull that out, and I'm going to have 7 left over from the 56. Sorry I didn't do this earlier. So I have a 2 on the outside, and a 3 times 3 times 7 from the 56. And 7 times 3 is 21, times 3 is 63 over the number 3. Now, one of the things people often confuse is they think that they can reduce this 3 with this 63. But this is inside a cube root, so really it's being raised to a power. It happens to be the 1/3 power, but it can't be reduced with this 3. Because this is inside, this is outside, can't reduce them. You could reduce a 2 and a 3 if you could, because this number is on the outside, but they don't reduce, so you're done. There is your final answer. All right, let's take a look at these. You could do these in different ways, but I suggest you actually make sure first that they have the same denominator, if possible, and then deal with the powers. Now, in this case, it's a power raised to a power. What do we say we do with a power raised to a power? We multiply the exponents. Well, what is 1/4 times 4/3? Well, the 4's canceled, right? So you end up with 7 to the 1/3 power. Over here, I could rewrite 25 as 5 to the 2nd power raised to the 1/6 power. Now I have them with the same base, but this isn't just one power, so let's simplify that. I multiply exponents. 2 times 1/6 is 2/6 or 1/3. So when I multiply like bases, I add their exponents 5, not 25, 5 to the 2/3 power. So when you're multiplying things that are raised to a power and the bases are the same, you multiply by adding their exponents, not multiply the base and add their exponents. No. All right, let's take a look down here. Ignore that. We are raising this and this to the -1/2 power. Now, we know to deal, you could apply the -1/2 power and then move things, or you can take the reciprocal and make it a positive power. It's your choice. So if I took the reciprocal and changed it to a +1/2 power and then applied it, not a problem. The other way I could do it is I could apply the power. Remember, power to a power, you multiply exponents. Negative 1/2 times 4 is a negative 2. Negative 1/2 times 4 is a negative 2 power. And then to make this positive, I move it up. To make this positive, I move it down. So applying the power here, either way, it ends up as 5 to the second over 3 to the second, because 4 times 1/2, 4 times 1/2. And the end result here would be 25 over 9. Now I'm all done. Let's take a look at these two here. All right, when people see this, they freak out. No need to freak out here. The way I read this is 4 4th roots of 2 minus 5 4th roots of 2. How many 4th roots of 2 do you end up with? Negative 1. 4th roots of 2. Done. It's that easy. 2 4 to the 1/4 plus 4 4 to the 1/4 would be 6 4 to the 1/4 powers. This is, I think, our last one. Yes. So, again, this is much more complicated looking than it actually is to do. Okay, so I want notice these are smaller than these for exponents. 5/3, 2/3, 3/2, 1/2. 5 stays on top. The G is going to subtract with the bigger exponent, top minus bottom. It's always big minus small, so you can have a positive exponent. G to the 5/3 minus 2/3 is 3/3 or just 1. H, 3/2 minus 1/2 is 2/2 or just 1. So I can have a 1 on the bottom, oops, I can have a 1 on the bottom, or I don't really need it. The final answer is just 5G to the first, H to the first, or just 5GH. And that's it. And that was the homework, if you're with my class. Have a great day.